Good morning again. My name is Mike D. Lecluse. I'm president of Lesman Instrument Company. I'd like to thank all of you for taking time out of your busy schedules to join us for ASME boiler regulations and level instrumentation. In this 45-minute webinar, we will cover an introduction to glass gauges and remote level indicator technologies, some installation and positioning tips for water level instrumentation, some understanding of ASME code requirements, and preventing code violations. And then at the end, we'll have a question and answer session. Our presenter today is Jim Kolbus, product manager for the boiler trim product line for Clark Reliance, who he's been with for 34 years. He specializes in level instrumentation pertaining to R&D activities and engineering. He's earned his bachelor's degree in industrial management and mechanical engineering from David Myers College in Ohio. Jim's been a member of ASME for 25 years, an appointed member of ASME Research and Development Group for Section 1 SG-GR BPV-1 Committee, has been a member of the American Boiler Manufacturers Association, served on ABMA's Board of Directors from 2011 to 2014, and served as chairman of ABMA's INC Members Group and ABMA Associates Group, and is currently the chair of ABMA Technical Committee. Jim, thank you for joining us and sharing your experience. The phone lines are muted. If you have any questions, there is a question tool built in to GoToWebinar. Please feel free to type in your question and I'll make sure they get answered. With that, I'll turn it over to you, Jim.
All right, thank you, Mike. And as Mike indicated, our subject topic today is ASME requirements for boiler water level instrumentation. And we estimate this presentation to take between 35 and 45 minutes. And we're going to run through the following topics. We'll be talking about the various types of gauge glasses and remote level indicators. We will define the Section 1 requirements for those same devices. We'll discuss positioning of level instrumentation correctly on your boiler application. We'll discuss low water cutout devices, some of the helpful guidelines that are in Section 7. Most everyone is familiar in this industry with Section 1, general requirements, construction rules for power boilers, but Section 7 tends to get very little attention. And Section 7 was rewritten in the year 2015. It's about a 250-page document, and it has a lot of helpful information for many areas around the boiler, but we are, again, focused on level instrumentation. We'll also illustrate some common code violations that we see out in the field. Some of them are involving our own products, whether they be misinstalled or items in poor condition. So we'll get through that, and at the end we'll have a few comments and recommendations for users about this subject matter. When it comes to direct reading gauge glasses, there are 4 types. From left to right on this slide, you're looking at a tubular glass. Now, tubular glass is typically available in 5/8 or 3/4 inch outside diameter. The one illustrated here is on a tilted arrangement with those valves, and the reason the fluid looks red is because it has a red stripe on the glass that is magnified when water is in the tube. Tubular glass is rated to 250 pounds service or 1.7 MPa. The MPa designations are on here because that's what the boiler inspectors often like to go by. Tubular glass in our minds offers the least amount of safety because typical tubular glass has less than a 1/4 inch thick wall. And if neglected, the tubular glasses can get thin and get in a dangerous situation. However, if they're inspected regularly and if they become cloudy or they appear to where you cannot see through them, they should be serviced and replaced immediately. All the other type of glasses we will be talking about here next are either a 1/2 inch thick or 3/4 of an inch thick glass, much safer than tubular glass. The next one is identified as a prismatic or reflex type gauge glass. The industry standard for those is 350 PSI or 2.4 MPa. Prismatic and reflex are interchangeable terms for the same type of glass. That glass is flat on the outer side and it has a prism molded onto the inner side. The image shows the level up to the water line as black and the steam area up above as white. What is happening on a prismatic gauge is the prism reflects ambient light, or actually a light beam directed into the gauge. And when there's no water in the gauge, the prisms act like a mirror and reflect the light back. When the prisms are backed up with water up to the water line, what you're actually seeing there, and why the water looks black, is you are seeing directly into the back of the gauge. And the back side of the gauge is solid metal. In this case, it's either cast iron or carbon steel. So because you're just looking into the back of the gauge, that's why water level looks black, even though we all know that water is clear. The reason these gauges are limited to 350-pound service is because there is nothing to protect the glass on the inside. And if used at higher pressures, the prisms would erode, the glass would erode over time and could turn chalky white, and you would suffer an inability to read the level as well as glass erosion. So when we cross over 350-pound design, most users go to either the flat glass or the bicolor. On a flat glass type gauge that's shown there, or transparent, there's a glass on the front and the back side of each window. And the way that these gauges are viewed is the level is illuminated from behind. So quite simply, if you were to put a trouble light behind the gauge and look on the front side, you see the image that is shown there with the two star-like orange dots. That is illuminated with an LED light fixture that is aimed to just focus on the meniscus line. And these gauges are very easy to read. And you'll notice the two sections in the image overlap each other. And the reason for the overlap is that is an ASME code requirement that dates back to 1996, and that requires transparent type gauges, because water would show as clear and steam would show as clear, to display so that the operator never loses sight of the meniscus line. So as the water level rises in that lower of those two sections, it will carry over into that upper section, and no matter where the level is in that operating range between the two sections of glass, the operator never loses sight of the level. Those gauges are limited to 2,000-pound service by most manufacturers with various models. When you start getting beyond 2,000-pound service, it's very difficult for an elongated piece of glass and the associated gasket to survive such high service. So that's that type. The last type shown is a bicolor ported gauge that displays green for water and red for steam. There are individual ports of glass, and the light fixture on the rear side of the gauge creates the red and green colors. As the water level rises in the gauge, the red light is refracted out of the way and the green light refracted into place so that you see green water or red steam. Without an illuminating fixture behind this type of gauge, it would be a code violation because the operator could not readily determine the level. Any gauge glass of any of these types must be set up and fitted so that an operator has obvious visual discrimination to know where the water level or steam area is. So that covers the four types of gauge glasses. As we move on, one thing to note about gauge glasses, some gauge glasses that we'll call lightweight designs that are intended for process fluids are often designed with these structural webs like is shown here. That little web is in the middle of the viewing area of that flat glass gauge. Even though it has a port machined through it, it still can be an obstruction for the observer when they're trying to find the level, and it could mask the water level. If this type of gauge were on a process fluid, such as oil or a chemical with color, it would not be an issue. But what is important to note is this type of design is not permitted by ASME for use on a boiler gauge. No obstruction in that vertical slot that is supposed to be wide open for level viewing is permitted. So just caution users that if you happen to be in a large chemical or plant or refinery and you got many gauge glasses, that could be fine in the process side. The rules are different on the boiler gauges. When it comes to the bicolor gauges, I've advanced to the next slide. This is just a quick explanation as to how the ported gauges work. And the illustration of the boiler off to the right was taken at a paper mill with the ported gauge, and you can see the top port is red and the lower 5 are green. And the glasses on the front and back side of this type of gauge are actually installed on the gauge body on an angle as shown on the illustration to the left. So the glasses are actually, if you look at that V shape, they're 160 degrees apart as opposed to 180 degrees apart. And with the strategically positioned red and green lights, when there's no water in the gauge, the red penetrates directly through and you see a red circle. As the water rises with the strategic angle of those glasses, the red light is deflected out of the way and the green light is refracted into place where you see all green. This is not unique to our products. Everyone in the bicolor gauge glass business does this the same way. One note about bicolor gauges that once these gauges become contaminated, the first sign of dirt buildup or deterioration within the gauge glass is seeing a red crescent moon shape in what should be all green. The red crescent moon is indicative of the gauge becoming contaminated, and this transfer of light angles is no longer able to operate properly. The first plan of action would be to blow down the gauge with steam to see if it cleans the gauge internals. If not, then it's time to consider rebuilding that gauge. And again, at the bottom of that slide, all bicolor gauge glasses, ported type, must be fitted with an illuminator in order to comply with ASME code requirements, being the gauge installed in a operator viewing position so that they can discriminate easily between steam and water. When we advance now to remote or indirect level indicators, there are 4 dominant technologies that we find in the marketplace today. The one in the top left is a conductivity type device. And what you see there is the chamber, vertical chamber with the sensors installed in it that are selected and positioned either by the boiler OEM or the end user. And there's a panel indicator that can be mounted near the boiler or always in the control area for the operator. And there's a control unit in between those 2 devices. Down below is a differential pressure transmitter, and there will be 2 sensing lines going to a transmitter and then a repeater to the level indicator, which is generally in the control area as well. Some cautionary notes about differential pressure transmitters is they can be subjected to freezing conditions that can have adverse effects. Also, these products are not automatic. Those sensing lines do need to be blown down periodically. We have users who often report they do 0 maintenance on those sensing lines to a DP transmitter, and if any obstructions build up in the water leg coming from the vessel to the instrument, it can result in a restriction of flow that should flow freely from the vessel to the transmitter. And if that becomes restricted, we could be sensing and displaying a false level indication. However, differential pressure transmitters are low cost and have been used for many years. The guided wave is shown in the center. That's a guided wave, essentially a pulse transmitter. And there are many manufacturers in that business now. What we see happening in the future is more guided wave radar level detecting devices being employed on the boiler industry to replace many of the DP transmitters. and the conductivity device being used as the alternate technology to the guided wave. We forecast more guided wave being used for control, and the conductivity probe having all the redundancy of the individual sensors and the fairly large indicator for the operator. Operators really tend to report that they like that image and that device as their so-called reliable traffic light to operate the boiler. And as soon as something draws out a normal level, it gets their attention. The last type off to the right is a magnetic level gauge. Those also stemmed from the petrochemical industry some 50 odd years ago, and we saw them migrating into the boiler industry over the last 5, 10, 15 years. And there are some serious concerns about the use of a magnetic level gauge on a Section 1 boiler. Number one, I'd like to say a magnetic level gauge is an excellent product in the right application. Process fluids, acid tanks, feed water heaters are all great applications. However, when used on a boiler, it's important that the boiler have high quality water with minimal particulate in it, because the way that device works, there's a stainless steel float in the center of that stainless steel chamber, and that float contains a magnet. So what you have to be aware of is any particulate that is floating in that water can attach itself to the magnet, resulting in the float getting heavier, and the float could start to sink in the level and in the water and indicate incorrectly. We strongly suggest any user who installs a magnetic level gauge on a power boiler do routine inspections, at least annual, on the float by opening up the unit and inspecting the float. If the float is removed and appears to be squeaky clean, you've got excellent water quality and thereby not have an issue. But there's a wide variety of boilers in the marketplace. Sliding pressures, operating pressures can have an effect on the level reading because the float is designed for the specific gravity of the water that it's being used in. And we have a number of users report these things work very well if they run at steady pressures. The code, however, does have a 900-pound limit for the use of magnetic level gauges, and a few more items that I'll describe a few slides down further. On the conductivity probe system, I just wanted to illustrate typical system here on the left, the column with the probes. And generally, when selecting a conductivity probe system, you're going to mimic the full operating range of that boiler from low cutout down at the lowest probe up to at least high alarm. And what you see here in that leftmost photo is a number of probes clustered in the middle. And that's where the operator is supposed to be living with their boiler water, right near normal. So it makes sense to cluster the probes where I'm supposed to operate if I'm the operator. As you work your way out to the extremes, that's not where you're supposed to be. So if we're touching a probe that is a high alarm or a low alarm level, the operator's job is to get that level back to normal. So there's really no reason to have fine resolution all the way to the uppermost level detection point and all the way down to the lowermost, because you shouldn't be operating there. The control unit, what you see here, this is our newer model, but typically there's one level sensing module for each probe. So each probe is individually operating with an individual brain, making this technology quite reliable. And of course, the panel indicator off to the right. Next slide. Now I'd like to get into a few details on magnetic level gauges. Magnetic level gauges are code permitted up to 900-pound service. So any application with your boiler with a maximum allowable working pressure greater than 900 PSI, you are not permitted to put a magnetic level gauge on it. Only up to 900. External switches, which by typically all manufacturers offer clamp-on switches that are mounted to the chamber at any desired location. And ASME code views these switches too easily mounted in a wrong location. And if you look at that illustrations off to the right, you'll see the magnetic level gauge identified as for power boilers. you need that vertical leg at the bottom of the unit extending below the lower branch that would go to the boiler in order to accommodate the typical length of the float. So you might say that's a dead leg vertical down below. And if someone were to casually mount the switch too low, they could accidentally have a switch mounted where the operator has no business operating the boiler. So to eliminate that risk, ASME does not permit the use of any switches on a magnetic level gauge for control functions. That's covered in PG12 and in PG60. Those are referenced to two separate sections within Section 1 of the code. My last comment on this slide is you'll notice the two illustrations off to the right, and the one that indicates for process, I would invite any of you to go looking on the website at magnetic level gauges, and you will see the indication scales extending into and above or below the two process connections. And if you think on a process application such as a tank of oil sitting there, that if there was always a dead leg of fluid indicated down at the bottom that can't drain back to the vessel, there would be no harm, no foul if this is just a unfired vessel with a tank of fluid in it. But if it's a boiler, we've got a very serious condition if an operator thinks they have water that they really do not have in the boiler. So you'll notice on the illustration to the right, the indication scale does not intersect the branch connections. That is an ASME code requirement. And we do see this error on boilers from time to time where users see the magnetic level gauges in the process part of the plant and apply the same technology on the boilers, not knowing that this indication scale is an important rule. So you never want to have a gauge indication scale that's so high that the fluid cannot fill there, and you never want to have the scale going down so low that it's indicating level that cannot drain back to the vessel. Next slide. Some of these issues, I'd like to summarize the concerns for magnetic level gauge. So they are acceptable as an indirect reading device to 900-pound service. The indication scale, as we just described, must follow the ASME guidelines in PG60. You may not install any accessories on a magnetic level gauge, such as a gauge glass. By doing so, you're making a water column out of that device, and the clearance is rather small in typical magnetic level gauges between the outside diameter of the float and the inside diameter of the chamber, and there is some potential risk if there's contamination buildup of flow that would go in and out of another set of branch connections if they were welded onto that chamber to support an additional level indicating device. So quite simply, ASME does not permit any additional accessories to be installed on a magnetic level gauge. And also stainless steel, as those chambers are, is not a permissible material for the construction of a water column. So no accessories. And the use of a magnetic level gauge does not replace the code requirement for a direct reading glass on any Section 1 power boiler. The reason I say this is I'd like to jump back to a typical process, refinery, or chemical plant where they may have hundreds of level indicating devices out in the process part of the plant, and they may only have a handful of boilers. It's very common to eliminate some glass on applications in the process part of the plant and install devices like magnetic level gauges. However, as you'll see in a few slides, ASME boiler code requires a gauge glass on every Section 1 power boiler. So if a user removes a glass and installs a magnetic level gauge like they may do in a process part of the plant, if they do that on a boiler, they're setting themselves up for an immediate code violation. And if their inspection authority, be it their insurance inspector or state inspector, sees that, it will be an immediate violation. Okay, Why the limit on the 900 pounds for magnetic level gauges? This is quite simple. If someone is, and I'd like to take an example. Let's just say we have a boiler designed to operate at 1,500 pound service. And if we were to take an example of a 60-inch diameter drum, and we have it operating half full at about 30 inches, and we change our operating conditions today. The load is less, and I need less steam, and I start operating at 500 PSI instead of 1,500. In that scenario, my magnetic level gauge would read high by 5 inches because, as I mentioned earlier, the float is designed for the specific gravity and operating conditions of the boiler. It would operate accurately at the 1,500 it was intended to operate, but if you have a big operating pressure drop, the amount of level indicating error can be quite serious with a magnetic level gauge. So if you're code committee and looking at these type devices, if you limit the pressure to 900 PSI, what you're left with is industrial and power boilers that are generally going to run at 75–80% of their design pressure and run steady, and the risk for these big process pressure swings is almost eliminated, and the risk for false indication is greatly reduced. So that's the reasoning behind the 900 pound limit. And the cautionary note is if the user has poor water quality, you have a greater risk for particulate buildup on the float, as I mentioned earlier. When it comes to remote level indicators, no matter which manufacturer is being considered or used, differential pressure or guided wave, in particular, we encourage you to check your OEM instructions for installation, programming to make sure that what you've done is accurate. There are some rules about insulation. There are some rules about leaving the condensate pot exposed on differential pressure transmitters. All these things need to be considered per the original OEM's recommendations in order to get an accurate reading. Precautions must be taken on these devices to guard against freezing conditions. And there can be some serious consequences if water level devices that may be installed indoors or outdoors in difficult climates in the winter months if they're not heat traced and guarded against freezing. Insulation. I'd like to recommend insulation on all the piping leading up to the instruments and up to the gauge glasses. This helps accomplish a couple of things. It provides personnel safety by improving the insulation on that piping, reduces accidental risk for burns by someone brushing up against a hot pipe. It also reduces the amount of condensate that forms in some applications, and that can be beneficial to extend the life of a gauge glass because excessive condensate formation can be sort of mimicking constant power washing on the inside of a level instrument or gauge glass, and if there's any particulate in that water, that could be raking across the glass or mica shield on the inside of those high pressure gauges, which in effect shortens the service life. Any level instrument or gauge glass by itself is going to be the furthest item extending out from the boiler, and by its nature, it will condense from top to down to the water line. So if you insulate all the piping leading up to it, you control that amount of condensate and help it from being too excessive. All right, next slide. Now we'll start to get into the real code minimum requirements. And I say minimum because what we're about to describe is code minimum, and there could be additional instruments installed to back up these minimum requirements. If you have an extra gauge glass or an extra indirect or remote level transmitter, then if one of these code required devices are out of service for maintenance, you're still in compliance to operate. So to carry forward on minimum, any boiler operated up to 400 PSI must have at least one direct reading gauge glass on it, must be in service at all times. Doesn't matter if you had 20 transmitters on that boiler, the gauge glass will be in service at all times. Once you cross over 400 pounds operating, the owners actually have 3 choices when it comes to level indicators. You can have 2 separate gauge glasses in service at all times in such a way where the operator is positioned to see them 24/7. That could be located out in front of the boiler, that could be with TV cameras on them, but this is probably the one that's been in force in code for many, many years and probably least used today, because nowadays the operator's sitting in a modern air-conditioned control room looking at a panel of instruments and not stationed out in front of the boiler itself. So the second scenario listed there is 2 remote level indicating devices, separate devices on continuous display for the operator, combined with the 1 required gauge glass. And the gauge glass can be valved off, but it must be maintained in good working order. Now, what we often see here is 2 remote level indicators for that operator sitting in the control area. And what's important to note is if they need to change any screens around to operate or maintain other parts of the plant, the level indicators must be set up so that they do not disrupt constant display of the level indicators. If they need that screen for another device, then level indication should be set up like a toolbar on the bottom of the screen so that you don't lose sight of it. So the gauge glass is being valved off. In that example, we typically see that when pressures are exceeding 1500 PSI. Even though the code allows you to do it over 400, many users, plant rules, insurance companies like to see gauges in service at many of the pressures. And I would say, even though it's not a code rule, once you start getting over 1500 pound steam, you're getting into a very harsh environment for any gauge glass. And most users, when you get into those extreme higher pressures, tend to valve them off, keep them in working order, and use them only when needed. If they get an upset condition between one of the 2 transmitters, they have something to go check against. And that idea of having that extra device being the glass that you can confirm your water levels is one of the main reasons why gauge glasses will not go away on power boilers. The last option would be to have a gauge glass, whether they can view it directly from where the operator is stationed or with the use of a TV camera, and 1 remote level indicator, be it any of those 4 types we described. And the end result is wherever the operator is positioned, they have 2 separate devices to look at level. And that jumping back to that top one up to 400, if the operator can't see the gauge glass where he's located, he or she, even though you're not permitted to shut it off, if they can't see the glass, they've got to have 2 transmitters on display in front of them. And in summary here, if you put yourself in the shoes of the operator, if all you can see is 1 remote level indicator, not being a glass, how do you know it's correct? If I have 2 remote level indicators, I've immediately got checks and balances. If the 2 level indicators are tracking with each other as the level moves up and down, maybe they're not reading identically, but if they're within some small fraction of an inch, then the operator is highly confident in knowing where that water level is. Okay, our next slide shows us positioning of a level instrument. And what we're looking at here is a gauge glass and the visible range for that gauge glass. And the important things, I want to cover 2 rules here. One is when you look far left, there's a level A. If we get below level A, we are risking damage to the boiler internals. So level A, what we'll say, is the danger point as determined by the boiler manufacturer. We get below level A, we're exposing those heating tubes that's kind of illustrated below level A, and we absolutely cannot operate there. So the first rule we'll talk about in the code is low vision, position number 4. Position number 4 must be at least 2 inches above level A. So the operator can believe as long as I've got water in the gauge glass, I'm okay, I'm out of danger. So That's a very important rule. The gauge glass be located at least 2 inches above the danger point. The original boiler manufacturer is responsible for placement of that glass on that boiler and those recommendations. The second set of rules here is that low vision point in the gauge glass, item 4, cannot be any lower than item 2. Item 2 is the high side exterior of the water outlet coming off the vessel. Now, to make all this come together, that 2, and the level A rules have this 2, or excuse me, the 4 not intersecting 2 and staying 2 inches above level A have to both be enforced. And on the high side of the gauge glass, item 6, high vision cannot be any higher than item 1, which is the low side of the steam outlet coming out of the vessel. So on one hand, you position the gauge glass within those rules, but the comparison of locating the bottom of the gauge to the reference of the level A is a must. All these rules have to be looked at as a whole, not just one by itself. All right. Next slide. We're showing a comparison here of the same things we just discussed, but I also wanted to highlight the magnetic level gauge, that indication scale on a magnetic level gauge must follow those same rules as a gauge glass. Again, I highlight this because we have seen some users migrate magnetic level gauge technology in the same way they have it in the process part of the plant and create some violations. So that indication scale cannot encroach into those steam and water outlets coming off the vessel and must meet that level A 2-inch requirement. This next slide is quite busy. I'm not going to get into a lot of detail in each of these things, but what I've done here for all of the readers and participants today is highlight the subsections within section 1 of the code where you can find these details if you have a specific question. If you're installing a water column on a boiler, those first references are identifying the minimum pipe sizes for the vessel connections and the drain piping. On the water level indicators, no matter what type, these rules we've been discussing to this point are all identified in those subsections. And the one note down near the bottom, second one from the bottom, gauge cocks, those are referred to as those 3 valves that are shown in the image in the upper right-hand corner. Those valves vent to atmosphere. When you tug on a chain, you'll see a plume of steam or a stream of water, almost like it's coming out of a garden hose. And for many, many years, that was a very easy way of confirming water level. Well, back in 1991, Code Committee realized and reviewed some data that gauge glasses are very reliable in these low pressure boilers, that these gauge cocks were commonly used, and the rules changed for boilers up to 400 PSI to simply state that a gauge glass must be in service at all times. Prior to 1991, you were required to have 2 gauge glasses or a gauge glass and a set of those 3 tricocks, and it's been reduced down to simply 1 gauge glass up to 400 PSI. The last comment there is regarding safety ball checks in the water gauge valves, and they are considered to be a code option, not a requirement, and that's covered in the appendix of non-mandatory items at the end of section 1. And so ball checks, while they are a very good thing in process fluids and hazardous chemicals and fluids, boiler water by itself is not considered a hazardous chemical, and they can actually restrict the flow of water and steam through the gauge when owners and users try to conduct blowdowns to keep the gauges clean. So they become an owner choice by section 1. If you wish to use ball checks, you can. They are not required, but if you do, there are some specific requirements for the installation of ball checks. Some other section 1 requirements for valves: any level indicating instrument must have isolation and drain valves, And if you choose to have valves between a water column and the boiler, in that location, they're optional. But off of a water column, which typically supports a gauge glass, every remote level indicator must have a set of isolation valves. But back on water columns, and we were looking at some illustrations earlier of the drum and a water column and then the level instrument, the valves between a water column and the boiler are optional. However, if they are used, they must be physically locked open to prevent unauthorized use, and someone in the control area would be the main responsible party for that locking device. All right. Also, drain piping coming off of any level instrument should be routed to a point of safe discharge. And just a comment on that, a point of safe discharge is not a short pipe stub right beneath the level instrument that's almost aimed towards an operator's feet when they go to manipulate those drain valves. Usually it could be routed to a condensate return system or at least directed away from the operator who will be manipulating those drain valves. We strongly encourage installing chain. The code requires an operating mechanism on any gauge glass valve set to the platform or operating floor, and especially when any valves are more than 7 feet above the platform. If a valve is within 7 feet, a typical operator can manipulate it, but if it's greater, the only way to get to it is either with a ladder or a chain. Obviously, a mechanism such as a chain or reach rods or electric actuators would be a safe way to manipulate those valves. One comment about globe valves is globe valves are required, or can be used, I shouldn't say required, for isolation and drain. What I show in the middle of this slide is an incorrectly installed or incorrect type of globe valve. Typical standard globe valves have the potential of a sediment trap, as is shown there. The correct type of globe valve shown off to the right could be rotted through with an extension rod, and this would enable the user to easily inspect the valve and, most importantly, prevent any sediment trap from building, restricting the flow of steam or water into a level instrument. So if you choose to use a globe type valve, it must have at least 1/4 of the inlet port diameter above the seat when the valve is open. There are some companies, just to mention a couple of names, Conval, Everlasting, who make these valves in code compliant models. On low water cutouts, there's a separate ASME publication called CSD1, Controls and Safety Devices for Automatically Fired Boilers. When it comes to low water cutouts, they require 2 separate devices, one primary and one secondary. Each of those devices can share the same steam nozzle feed coming off the vessel, but they must have separate water feed nozzles coming from the vessel. In the event that one water leg gets restricted, it would not take out both devices. Minimum piping is 1 inch. Minimum drain size is at least 3/4 inch on these devices. When it comes to low water cutouts, here's just a few illustrations. They can be conductivity probe type. They can be float actuated. They can be externally mounted to a water column. And most commonly, water columns often have probes installed vertically in the top, as is illustrated on the bottom center. And what you see there is where the tips of those probes end. That's the actuation point. As the water rises and touches the tip of those probes, we complete a conductive path with the properties of the water and energize a signal so that the operator knows there's water at least at those levels. And when the water drops below those lowest probes, that's typically going to be your low fuel cutout. Now we'll get into a few common code violations and concerns that we see when we're talking to users, surveying plants, working with boiler inspectors. The things that we commonly see are contaminated or inoperable water gauge glasses. Maybe it's red tag, do not operate, and it's been too long a period of time since that was done, and it too much time has gone by without it being remedied. Missing light fixtures from ported style gauges, missing gauge glasses in total. Maybe someone installed a magnetic level gauge to replace a gauge glass. Inadequate display of remote indicators in a control room combined with an isolated gauge. What I mean by inadequate display is the need for an operator to strike a key for that information to come up on their screen. That would be, as we said previously, inadequate. Poor maintenance practices. Really, there's no excuse for this anymore. There's too much information out there on the web. If anyone has any doubt when servicing any of these instruments, we strongly urge you to seek out that original equipment manufacturer, find their instructions for torque values of fasteners, operating procedures, insulation, advice on the sensors themselves. Seek out the original manufacturer. They know best about what they recommend. Plus, replacement components improve over the years. It's always best to go back to the original manufacturer. Here are a couple illustrations of code violations I'd like to share. And the one on the left, the red arrow is pointing to where a drain valve is supposed to be on that lower water gauge valve. And what this user did was they welded it shut. So when they close that upper and lower valve, the handles are pointing back away from the valves. There is no way to relieve the water or trapped pressure that's in that gauge glass. So that was a serious error. The one on the right is a magnetic level gauge that was installed on a power boiler, and there you can see that water level is indicating below that lower horizontal connection with the valve that you see there. That is the water feed to that level indication device. So there's no way for that lower vertical part of that mag gauge to drain back to the vessel. So it would always show a little bit of water there no matter what reality is in the drum. This is a slide of a typical package boiler, and what we're looking at on the left are two gauge glasses attached to a water column. You can't see the levels in those gauge glasses due to the angle of this photo, but assure me they were operating correctly. And you can see chains connecting those valves together that are properly installed. And there's drain piping coming off of those lower water gauge valves right alongside those chains. Going back to the water column behind the right-hand gauge glass, there is drain piping coming off of it, and actually everything's pretty good on that side of the drum. When we go off to the right side, we are seeing some missing insulation on the piping, and we see a condensate pot and a lower connection with the two tubes, silver-colored tubes coming down. Those are the sensing lines for the DP transmitter. Off to the right is a conductivity probe device. The problem that happened here is that U-shaped trap in the piping above the red arrow one day began to clog with sediment in this particular application, and both of those level transmitters were reading higher than the actual level in the drum because that trap became restricted. Operator happened to be out on the floor, looked at level just about to flirt with low water cutoff, and they were seeing above normal on the two transmitters. So what they ended up doing was blowing down that trap through the drain pipe that you see on that conductivity probe column way off to the right, and then immediately a bunch of particulate blew out the drain, and both of those transmitters responded with a much lower, more accurate level. Come to find out what happened where that red arrow is, at one point there was a longer pipe extended and a drain valve. One day the drain valve failed, they needed steam, and someone made a decision to just plug it and we'll replace the valve when we get a chance. And when we get a chance never happened, and resulted in both of those transmitters reading incorrectly when that sediment situation occurred. So it has since been remedied. I don't have an after photo of this one, but you understand what the concern was. Now here's an installation error that was very serious that occurred on a new installation. That water column and gauge glass was supposed to be mounted right after the two double isolation valves that you see coming off of the drum on this brand new boiler installation. Well, what has happened here, someone made a decision at the job site to relocate the water column so that when an operator climbed the stairs onto this platform, looked across the head of the drum, they would look over and see the level where that red line is in that application. Well, in order to do that, the installer put those offset piping in on the steam and water connection and dropped the elevation and lowered the elevation of that entire water column and gauge glass. By doing so, they created a water trap level indicator, putting that gauge glass in a very serious location. So had they run the boiler with that incorrectly mounted water column, we could have put this brand new boiler at risk. So we saw this, we were made aware of it, we recommended to the customer immediately to cut that off and put that water column back where it should be. And you'll see here in the next slide, the water column was remounted correctly where it needs to be on those original connections. And in summary here, we built the water column correct, the contractor did their job correct, specifying the water column. The field contractor decided to make their own decision where to mount that water column and almost put that brand new boiler at risk. Just an example of what can go wrong. Here is another violation where we have a before and after. There's a bicolor gauge there on the left, ported type with no illumination on it, and it's virtually impossible to read the level. The one on the right has been retrofitted with an appropriate illuminator and viewing hood, and you can see the first 4 ports are green, the top 3 are red, and easily read that level. I mentioned at the beginning we were going to touch on section 7. We're running just a few minutes longer than I anticipated, but we're nearing the end. Section 7 is this recommended guidelines. Again, not a code requirement, but an ASME recommendation that operators should check instruments, 2 or more of them, to check the level prior to startup. Operators should keep gauge glasses clean so that there's no deviation that could be mistaken as level. Gauge glasses should be properly illuminated. Cautioning that blowing down these devices, opening the drain valve excessively, meaning too long a duration, we recommend 20 seconds as a maximum duration. If 20 seconds doesn't clean a level instrument, minutes is not going to do any better. In fact, it will do more harm by wearing and tearing away at valve stem packings from within the center of the valve rather than trying to help yourself. And checking your high and low alarms is critical. That's obviously going to prevent boiler damage and carryover in the steam output. Here's a quick recommended procedure for conducting a blowdown, and what we're pointing out here is if operators simply just open drain valves, which is a very common practice, if you don't do anything to isolate the steam to flush the water leg coming off that drum, steam and water will both fight their way to go out the drain. So if all I do is open a drain valve, that alone is not a sufficient blowdown. However, if I close valve 1 and 2 and leave 3 and 4 open and then open my drains, I am certainly flushing the water line and any debris that may be in it. Then close those or leave them open and then open the steam valves and then return everything to normal. But the idea, the concept here is to isolate the steam valves, blow the water lines down, then you could isolate the water, blow the steam down, and then return everything to normal. The reason for blowing water first, steam second, is to clear any debris, and then with the steam, flush any debris out the drain. And this is the same discussion, but with only a remote level indicator instead of a gauge glass. So our summary, last couple slides, and then we're done. Summary recommendations for modern technologies is to use LED lighting, and there's really no excuse not to apply LED lighting. Most all the level instrument manufacturers are offering LED lighting for about the past 10 years or so. That eliminates the nuisance of incandescent or halogen bulbs that would burn out frequently, and also for just a fraction of the operating power. So there's no reason not to have a gauge glass properly illuminated. When you're applying remote level indicators onto your boiler, using multiple technologies will guard you from a single component or single design failure from taking both of your level instruments down. Very likely, if you have the same technology on your boiler and two of the same, and if they were both manufactured at the same time, if there ever is any kind of issue, that could affect or compromise your reliability. But if you have, say, a conductivity probe device and a DP transmitter, or a conductivity probe device and a guided wave, you've got two technologies operating on different principles, and your reliability is that much better. Conduct proper maintenance and regular inspections of these instruments. Look for leaking valves, missing insulation, deteriorated level instruments. Any obvious flaws should be taken care of before any damage occurs, whether it be steam cuts or personnel risk. Recommendations for the specification: always identify that any instrument you're installing is code compliant. Examine the piping, as I just mentioned. Consult with your insurance underwriter or plant safety department or state inspector to verify what they want you to have as a minimum requirement in your particular plant. We've discussed here today the minimum code rules, and your individual plant may have rules exceeding code minimum, your own so-called plant rules. And again, always follow OEM maintenance instructions for the most accurate, most current, and most reliable information. So as I wrap up here on my last two slides, top questions for you to think about within your own plants are you having any operational issues with the gauge glasses or remote level indicators on your boiler? Consulting with the operators and the operations personnel and maintenance personnel are the best people to consult. What instrumentation are you using in the control area for your operators? Are your limit controls on your boiler operating properly and tested regularly? And making sure that every level instrument on your boiler meets or exceeds the design pressure, maximum allowable working pressure of your boiler. Finally, we'd like to thank all of you for your time today. We offer a little booklet that is a boiler inspection guideline. It's a little 5x7 book. It is a publication that we update annually. These are available at no cost to you by contacting Lesman and or Clark Reliance. And there is no cost for this book. It's a little subset of the code. It highlights many of these things we discussed today. So again, I'd like to thank all of you for your time. I apologize, we ran a few minutes longer than I anticipated. And I'd like to turn it back over to Mike, and if there's any comments or questions.
Jim, you obviously did a great job, because so far I don't have any questions that have come in. Thank you very much for your presentation. If any of the audience does have specific questions, please feel free to give us a call at 800-9-LESMAN or 800-953-7626. If you don't know your account manager, please feel free to ask for me, and I'll make sure that you get taken care of. You can also send me an email at miked@lesman.com. If you want to know more about the technologies we supply, please follow us on social media. Dan's blog is active and has a lot of great tips. All of our webinars are posted both on our website and on our Lesman Instrument Company YouTube channel. If there are some topics you'd like us to cover in our webinars, please send me an email with the subject. We have access to lots of product specialists like Jim. Please let me know, and we'll see if we can bring a specialist onto a webinar. At this point, there aren't any further questions, so we will conclude. Thank you very much for attending, and Jim, thanks again for the presentation. It was great.
Thank you.